This video is going to attack molecular orbital theory, which is an extension of valence bond theory. Valence bond theory provides an excellent model in agreement with observed molecular geometries, but physical properties such as magnetism cannot be explained. So we need to expand on this valence bond theory. And molecular orbital theory, which is abbreviated MO theory, depends on, and there are two main factors. One, the energy of the orbitals interacting, and two, the shape or symmetry of the orbitals interacting. Okay, the shape or the symmetry is going to depend on if we have a particular s orbital interacting with an s orbital, that's going to be greater or different than a p orbital interacting with the p orbital. Or if this is a pz orbital, it's going to have a different interaction than the py orbital would. Okay, so this overlap is going to be much different here than it is here than it is here. And we talked about sigma and pi bonding, and actually when we have these sigma and pi bond forms, we're going to have a great difference in energy. Also, if you remember the energies of these orbital diagrams, a 1s orbital is very low in energy, followed by the 2s and the 2p. So the 1s orbital is so far down in energy, and if we're looking at something like an oxygen, 1s orbital is going to be a core shell. So the valence electrons are going to be the 2s and the 2p. And the reason that the valence electrons interact is they're going to have the appropriate energy to interact with other valence electrons on an adjacent atom. So we typically just look at the valence electrons in this molecular orbital theory to determine how the resulting energies are going to be for our molecular orbitals. So let's look at the different interactions or the orbital overlap that can occur between two s orbitals. So if I have an s orbital over here on the left-hand side, and I interact this with an s orbital over here on the right-hand side, if they are the same atom, say an oxygen atom, I have an energy level of one of the s orbitals that are over here. Or if we look at something like hydrogen, we're going to have 1s orbitals at the same energy. When they come close to each other and they form, they're going to form a bonding molecular orbital, which would result like this, and an anti-bonding molecular orbital, which has the destructive interference. Okay, so we have a bonding molecular orbital and an anti-bonding molecular orbital. And we can characterize this, if it's a bonding molecular orbital, we have head-on overlap, we can say this is a sigma, and the anti-bonding orbital is going to be something called a sigma star, indicating that that is anti-bonding. Okay, in each case we have head-on overlap. One of the things that we can say is that when two atomic orbitals overlap, two molecular orbitals are formed. So the sum of the atomic orbitals must equal the number of molecular orbitals. So this is going to change a little bit when we look at p orbitals, because there are 3 different types of p orbitals, and we can look at how they might interact. So if we look at, say, the 2 p orbitals on oxygen, in an atom those are degenerate, and we have the px, the py, and the pz. They're all going to be the same energy. If we take 3 more p orbitals on the same atom and overlap them, for example, if we're going to form an O2 molecule, we have the px, the py, and the pz from the next oxygen atom. So if this was oxygen atom number 1 here, we have p orbitals that are going to look like this, and ones that are going to look like that. On the adjacent oxygen, we're going to have p orbitals like this, and ones that go like this. So these are each of these orbitals, and typically when we represent them in these cases, we break them apart and draw them separately. So we have one p orbital that looks like this, one p orbital that looks like this, and a third p orbital that's going to be rotated 90 degrees from that. So as we can see, the overlap here is a head-on overlap, which is going to result in a sigma bond, and the overlap between these guys right here is going to be side-on. So we're going to result in a pi bond forming. And for these 2 instances, the overlap is equal, because these p orbitals are just rotated 90 degrees in space. Okay, so if the overlap is equal, then the energy is also going to be equal. So when we form these bonding and anti-bonding molecular orbitals, the strongest bonding molecular orbital that's going to form is going to come between the 2 pz orbitals, which is going to look something like this. So 2 orbitals of the same phase interact, and our anti-bonding molecular orbital is going to be the exact same picture, but with opposite phases. Okay, so that's going to take care of each of our pz molecular orbitals. Okay, because in each case we have now 2 molecular orbitals. There are 1, 2, 3, 4, 5, 6 total atomic orbitals, so we need 6 molecular orbitals. The overlap that forms next, and the resulting diagram is going to look something like this. And this overlap is going to come from the same phase py orbitals interacting, as well as the same phase px orbitals interacting. So when we draw the pictures of each one of these, we're going to see overlap that looks something like this. Okay, so here we have a pi interaction, here we have a pi interaction. The overlap is the same, and that's why each of these orbitals are at the same energy down here. Okay, so here we have a sigma bonding interaction, here we have a pi bonding interaction, and since this overlap is the same, these orbitals are degenerate, or they're going to have the same energy. So the same thing happens with the anti-bonding interactions, where we're going to have interactions where we have these p orbitals with opposite phase that are the same interaction but located differently in space. Okay, so this is going to give rise to the pi star or the pi antibonding, and the sigma star, or sigma antibonding. This is the overall skeletal structure that we're going to see when we put these molecular orbital diagrams together. So let's go through, and when we look in the next video, we'll discuss what these molecular orbital diagrams look like for these molecules, and we'll begin to populate these molecular orbitals with electrons.